In this video, we'll go through how to measure and characterize non-idealities of various capacitor types via an impedance measurement. From these impedance measurements, we can then extract parameters such as capacitance, equivalent series resistance, equivalent series inductance, and self-resonant frequency for modeling and simulation purposes. Throughout, we will compare between SMD multilayer ceramic capacitors, tantalum and aluminium electrolytic, and explore their similarities and differences. Finally, I'll show you how to import these measurements into LT-SPICE and compare the simulation to reality. For impedance measurement, we will be using the Omicron Labs Bode 100, which is a very capable low-frequency vector network analyzer, in conjunction with B-SMC impedance adapter, shown on the bottom right-hand side, along with the Bode Analyzer Suite software to perform real-time measurements. I'll show you about measurement technique, calibration, and then performing the actual measurement itself. This video is the start of a video series where we explore impedance measurement, so make sure to stay tuned for future videos on measuring real PCB decoupling networks, their impedance profiles, regulator stability, and much, much more. A huge thank you to JLCPCB for sponsoring this video. For this video series on impedance measurement, I've created many different PCBs and had them manufactured and assembled by JLCPCB in China, and they've done an absolutely fantastic job. JLCPCB has in-house PCB production, in-house component sourcing, and in-house PCB assembly. In my eyes, they are super affordable, have pretty awesome capabilities, and are incredibly fast. For instance, some of the test and measurement boards we'll be using in this series of videos are got manufactured and assembled and shipped back to me within about a week's time, which is pretty incredible. I'd strongly suggest checking them out. Links to JLCPCB will be in the description box below. A huge thank you also to Altium for sponsoring this video. If you'd like to give the powerful Altium 365 platform a try, make sure to follow the link in the description box below or go to altium365.com/YT/PhilsLab and you can get yourself an Altium 365 free trial. Altium 365 brings many impressive features to Altium Designer, such as collaborative design reviews, mechanical co-design with SolidWorks, Fusion and more, manufacturing collaboration, ease of BOM management, and much, much more. If you'd like to check out in part some of the cool features of Altium 365, you can also go to my GitHub profile and my GitHub IO page, pms67.github.io, and check out some of the example hardware designs that were shown on the YouTube channel here. With the Altium 365 viewer, you can explore the boards in your own time and in real time. You can look at the 3D models and you can scan through the PCB layers as well as the schematics on some of the designs. I'll leave links in the description box as usual. The first question we have to ask ourselves is, why is this even important? Why do we need to make measurements and model certain circuit elements, for example, capacitors, resistors, and inductors? The reason quite simply is that real-world capacitors are non-ideal. Although you might just see a capacitor circuit symbol on a schematic, there are many items and parameters, oftentimes non-linear, that actually characterize that specific capacitor. Those parameters might be the tolerance itself, so you might have seen plus minus 20% tolerance on a capacitor, so a 10 microfarad nominal capacitor might range anywhere from 8 microfarads to 12 microfarads. Then we have derating. For instance, applying a DC voltage across certain types of multilayer ceramic capacitors actually reduces the capacitance quite drastically. Similar things happen for an AC bias. AC signal applied across the capacitor. We have derating for temperature, as well as aging of the capacitor. In addition to just the capacitance itself, we also typically have equivalent series resistance, which is ESR, as well as ESL, which is equivalent series inductance. And we'll get to the model later on, but you can really see a hint of that on the right-hand circuit equivalent. There are other non-linearities, for instance that the ESR isn't just a single fixed value, that there are other non-linear effects, and all of these non-idealities also depend on the capacitor type. Depends on what type of dielectric, what class, the package size, if it's SMD versus through-hole, and so on. Given that these real-world capacitors are non-ideal, these non-ideal effects have influences on all real-world circuits. For instance, for regulators, that is linear regulators or switching regulators, that might have an influence on the stability of the loop stability of the regulator. If the ESR might influence the output ripple, we see it as buck converter, as well as the noise. For filters, if we have these non-ideal elements, maybe at high frequencies, the cutoff frequency, bandwidth and attenuation will be different. For power distribution, if we think of capacitance between planes in a printed circuit board, or in addition to decoupling and bypass capacitors, this will give us some sort of impedance profile, which depends on these non-idealities and these capacitor parameters. Although in this video we will be measuring capacitors effectively on their own, all of these capacitors and non-ideal circuit elements interact with PCB features such as the traces, pads, and vias, which can cause issues in the real-world design. For circuits in general, and in particular for critical circuits, think of power, RF, or high-speed digital analog, we need to know these effects well ahead of time for simulation and to be able to do calculations so that we can adjust our circuit and compensate and make sure that the circuit will behave as intended despite these non-idealities. Therefore, it makes sense for us to measure and characterize these circuit elements. Now, of course, oftentimes the manufacturer might provide this data for you, but there are specific situations where you need to do these measurements yourself. Either the manufacturer doesn't provide this data, or you have very, very specific operating points. For our case, we're going to be doing it out of the previously mentioned points, but also, of course, for interest, and because this video is part of a larger series and will be a prerequisite for future test and measurement videos, where we'll be looking in depth at RC or RLC filters, we'll be looking at farad beads and pi filters, power supplies, looking at LDOs and switcher stability, ripple, noise, and more. We'll also be looking at power distribution networks, looking at the PCB impedance profiles, measuring the board impedance with bypass caps, looking at capacitor and capacitance resonance and anti-resonances, and all of these videos will build on videos such as this one. If you haven't already, as a primer to this video, make sure to check out video number 114 on my channel. A link will be in the description box below, which is entitled Capacitor Hardware Design Basics, which you can see as somewhat as a prerequisite or starter video to this one. Before we get to measuring a capacitor, we need to be familiar with how we want to model this capacitor. Now, there are many different types of non-ideal capacitor models. There are very, very complex ones depending on what frequency bands you might be interested in, what effects you want to monitor, measure, and simulate. So depending on the required accuracy, our complexity of that model will naturally increase. For the sake of time, and because this model is very, very suitable in many situations, we will be using one of the simplest capacitor models, which we also saw in the previously linked video. This model we can see on the right-hand side. On a schematic, again, we might just see a single capacitor symbol, we might see a part number and a value, but that will then translate after characterization to a non-ideal model we saw on the right-hand side. We still have capacitance, but that might be, of course, derated. We have a leakage inductance due to the leakage of the dielectric, which will allow a small leakage current to pass even at DC. We have the equivalent series resistance, and we have an equivalent series inductance. And this is one of the simplest capacitor models you might find. This is great because we can just use RLCs, so ideal circuit parameters combined together to form a non-ideal capacitor model. This specific capacitor model captures the essence at one specific operating point. So we have a fixed value for C, we have a fixed value for the ESR, ESL, and so on. Again, in many cases this is sufficient if you know and if you simulate your circuit at that specific operating point. For example, for a buck converter, that might be a specific output voltage, a certain switching frequency, a certain control loop bandwidth. Unfortunately, this model, as simple as it is, has some downsides. For instance, there are no parameter changes versus frequency, so the ESR and the ESL values are fixed for one specific frequency. We've computed the capacitance effect due to AC and DC bias only at a single point, again, which means for simulation we need to know the circuit operating conditions, and we don't really take into account the absolute capacitance value due to tolerance changes. So 10 microfarad capacitor, 20% tolerance, again might be at 8 microfarads or 12 microfarads or anywhere in between. Of course, for the simulation later on, we would then just assume a worst case for that specific circuit we are simulating. Lastly, for the sake of simplicity, in this particular video we will also ignore the leakage resistance, which we have on the top right hand side, which is in parallel with the capacitance. For this video we will ignore this. Another thing to keep in mind is that we are measuring the capacitor on its own. Of course, we have a test jig, a test setup, but for example, PCB mounting of a capacitor has, for instance, a large effect on overall inductance, and we might also get added effects due to increased contact resistance and parasitic capacitance of the pads. This is what we're not taking into account in this particular video, but it can be very important to keep in mind. If you followed video number 114, you will be familiar with that a capacitor impedance changes with frequency. And if we take our previous model and form the equations for the impedance of that model, we can get a curve as you can see on the top right hand side. We have a capacitive section from DC where we have this downwards logarithmic slope. Then we hit a resonance point, which is known as the self-resonant frequency of the capacitor, where both the capacitance and the equivalent series inductance cancel out, and we're left with the equivalent series resistance, and this is this minimum point, after which we start going into the inductive region of the capacitor where the equivalent series inductance dominates. This kind of graph is what you'll be seeing quite often when you look at capacitor datasheets and spec sheets. Capacitive region, self-resonance, and inductive region. So our task then later is for the capacitor measurement and model is to estimate the capacitance, and that includes AC-DC bias, temperature rating. We need to find the equivalent series resistance. Again, that's the value of impedance at minimum, self-resonance, as well as the equivalent series inductance, which we can find at the self-resonance or from the positive impedance slope after the self-resonance. And we'll come back to this slide to estimate these parameters, but you can also look at video 114 for a worked through example. Now keep in mind, again, this model of the capacitor is at one operating point, at one AC and DC bias, at one temperature, and actually the equivalent series resistance does change over frequency, and we will just pick it out at the self-resonance. Of course, we have to take care of these extra nonlinearities and non-idealities and simplify them down to our base model. Now to get slowly onto the measurement part, what we'll be doing in this video is threefold. Initially, we'll talk about some measurement basics, what techniques there are to measure impedances, that is for capacitors, resistors, inductors, and so on, and what limitations they have. We will just gloss over this very quickly. For this particular video, we'll be using a Bode 100, and I'll show you my test setup with this specific measurement equipment, as well as an impedance adapter. We'll go through the calibration and measurement setup in the software, and then we'll get to actually measuring a number of different capacitors and comparing them. So we'll measure the impedance versus frequency curves, that is the impedance as well as the phase, the magnitude of the impedance as well as the phase versus frequency. From these measurement curves, we can then extract the capacitance for our model, the equivalent series resistance, and the equivalent series inductance. Again, we'll do this for different capacitor types, so multilayer ceramic capacitors, tantalum, aluminium electrolytic, but we'll do this predominantly for SMD components because that's pretty much all I use on my PCBs these days, rather than through-hole parts. We'll compare different package sizes, what that might mean for ESR and ESL, voltage ratings and so on, and then also, for the sake of it, compare some of our measure data with the manufacturer-supplied data that you might find on their websites. After we've extracted all this information, of course it would be nice to actually create our own model, and we'll put that into a SPICE simulation, LT-SPICE in this case, and see how that compares. I briefly mentioned the Bode 100 by Omicron Lab. This is a very cool piece of equipment. It's a low frequency vector analyzer all the way down to 1 Hz up to 50 MHz in range, so quite different to your traditional vector network analyzer. It has a very large dynamic range. We can measure impedances which go into the megaohm region, but also down to milliohms and below with the right measurement technique. This particular instrument is incredibly useful for component measurement, such as we're doing in this video, and more generally impedance measurement. So we can actually use this to measure PCB power distribution networks, so PDNs. We can look at their impedance profile, we can look at power supply parameters such as power supply rejection ratio, stability, input-output impedance, and much, much more. And we will be doing this in many of the future videos. I can actually really suggest checking out Omicron Lab's YouTube channel as well as their app notes. I will leave them in the description box below. They are very, very well done. Now keep in mind, this Bode 100 is a fairly expensive bit of equipment, and there are of course other tools and techniques to extract component model parameters, such as a typical VNA. Although typical VNAs only have a frequency range that extends down to about 9 kHz, you could use an LCR meter or other methods of extracting capacitance, ESR, and so on. For this video, we'll be using the Bode 100 as this is the gold standard. With the Bode 100, here are some example measurement techniques and types that we could perform. We, for instance, have on the top left a one-port measurement, which simply takes the output of the Bode 100 and connects it to our device under test, which might be our capacitor, connected to the positive and negative terminals of the output. The output has a known output impedance of 50 ohms, so from this we can do a reflection measurement and impedance measurement and infer the impedance over frequency for this connection. There's also a 2-port shunt, which uses the output of the instrument and an input channel of the Bode 100. Or we could use an impedance adapter, which is an extra piece of kit that uses 1 output and 2 input channels of the Bode 100. I'll leave an app note in the description box below which goes over impedance measurement techniques using the Bode 100, which gives far more detail on when you should use one of these impedance measuring methods. We will actually be using 1-port and 2-port in future videos, but for this video we will be using the impedance adapter because it's very, very simple, straightforward, and its own test harness where we can put in capacitors, inductors, resistors without having to solder on any cables or wires. A quick diagram from Omicron Labs on the right-hand side shows that Depending on what impedances we want to measure and what impedance ranges, we will need to use different measurement techniques, so 1-port, 2-port, or the impedance adapter, or even something else, to make sure our measurement technique is suitable for the impedance range you want to measure. Shunt through, for instance, can measure impedance, of course with proper calibration, below 10 milliohms. If we use the impedance adapter, we can measure below 500 milliohms or over 10 kiloohms. So there are limitations of each, and you have to select the right tool for the particular measurement you want. Here's another graph by Omicron Labs, which shows in a nice graph form the limitations of these different measurement techniques when it comes to impedance analysis. The 1-port, which is this kind of yellowish beige, I'm not entirely sure what color that is, but we can measure up to about 10 kiloohms down to about 1 ohm across the 50 megahertz frequency range of the instrument. With a shunt-through measurement, we can measure far lower impedances, but maybe not very high impedances. And the impedance adapter, which is this bluish area, covers quite a large cross-section, but only up to about 1 megaohm and only down to about 10 milliohms. And that, of course, changes with frequency as well. So again, these measurement limitations are what we really have to be aware of. We'll see this impedance adapter later on as well. Here's a brief look into the impedance adapter. Again, we'll use the output of the Bode 100 and 2 input channels. The impedance adapter is essentially a holder for a component, so we can clamp in an inductor, capacitor, whatever you want to test. And this is known as the DUT, or device under test. What the Bode 100 will then do is inject a signal from its output, feed it through the device under test. Because we know the output impedance with the device under test and the shunt resistor will form a potential divider. So then we can tap off a point and measure the voltage on channel 1 of the Bode 100. And due to this shunt resistor, we can actually measure the current through the device under test because we know the output signal and we know the voltage across the device under test. So in this way, knowing voltage and current due to this impedance adapter, we can then infer impedance, which is simply voltage divided by current as a function of frequency. Again, for this particular adapter, given a proper calibration, the optimum impedance range is about 20 milliohms to 600 kiloohms. This can of course be problematic because many multi-layer ceramic capacitors have ESRs in the sub 10 milliohm range, which is outside of the optimum impedance range. Now that doesn't mean we can't measure it, but we might have some measurement inaccuracies. If we have very low ESR capacitors, it might be better to move to a 2-port shunt measurement, but for the sake of time and simplicity, we will just be using the impedance adapter in this video. Finally, before we actually get started with the measurement, here are some things to watch out for. Again, the impedance range is limited. Make sure you choose your measurement technique carefully. The frequency range is also limited, so we can pretty much go down all the way to DC, but we can only go up to 50 megahertz. If you're working on RF designs, a couple hundred megahertz, couple gigahertz, of course this might not be entirely suitable, but this frequency range is suitable for many power applications, many PCB applications. We always need to calibrate to remove the effects of cables, the impedance adapter, and our test harness. We don't have ideal connections going, for instance, from the output to the impedance adapter or from the impedance adapter back to the channel 1 and channel 2. Those wires and cables and connectors will have their own reflections, impedance mismatches, parasitic capacitances, inductances, which need to be nulled out with a calibration. The way we do this for the impedance adapter is perform an open, short, and load calibration. So open circuit, which is high impedance, short, close to 0 ohms, and load, a known resistive value. The calibration may not be perfect for these low impedance measurements. There'll be contact resistance, which will be very much in the order of what we're trying to measure, for example, in terms of ESR. This particular impedance adapter has a spring-loaded mechanism. The contact resistance will change depending on how much force we apply. So we need to make sure we're aware of these limitations and we apply consistent tests to this. We also can't directly apply DC bias to the caps, well, only within a certain margin. The max voltage at the output of the Bode 100 is limited to 3.3 volts because we have a 50 ohm output resistor at the output port, and overloading that with its power rating will damage the output. So when we're doing DC bias measurements, we need to use a separate DC block and a DC injector, which again needs to be calibrated for. We need to be aware of the cutoff frequencies and the non-idealities of the DC block. With DC blocks and DC bias injectors, you have to be careful when applying sudden pulses of DC bias, so when you're turning on your power supply, because that transient will and can pass through the capacitors and could damage whatever instrument you're connected to. So it will slowly ramp up the voltage of our DC bias. I know this was a lot of pretext, but now we're finally ready to do some measurements. So let's start with a measurement setup and then look at calibration. We'll start off without doing any DC bias injection, which makes the measurement setup very, very simple indeed. On the left-hand side in my rack, we have the Bode 100. On the right-hand side is an image of the Omicron Labs B-SMC impedance adapter. This impedance adapter contains a few different components as we saw previously and can house an SMD component. We have this spring contact which we can hold in place with this adjustable screw nut. And on the right hand side we have two contacts, one the spring loaded one on the left, and on the right hand side this plate which is just a gold contact plate. And by releasing the spring contact we can then clamp in an SMD component, which is exactly what we'll do. We can of course use this for calibration, where we do an open, where we keep the spring contact open, a short, where we simply push these two pins, these two contact areas together, and then a load where we'll put in a 100 ohm SMD resistor. The connections between Bode 100 and this B-SMC impedance adapter are simply I take the output of the Bode 100, feed it into the source input of the B-SMC, and the channel 1 and channel 2 markings of the B-SMC I just connect again with BNC to BNC cables to channel 1 and channel 2 of the Bode 100 respectively. So very straightforward, a clamping impedance adapter which can house our SMD components, our capacitors in this video, and with which we can perform the calibration. So now let's move over to the Bode Analyzer Suite, which is the software that accompanies the Bode 100 and is free for use. Here's the Bode Analyzer Suite. I'm running version 3.5 in this video. When I start this program up, I can choose the type of measurement I want to perform. I'm going to go to impedance analysis at the top, and we'll be going with the impedance adapter. We can use the through-hole impedance adapter or the B-SMC, which is the SMD version which we saw previously, and then we can select the measurement. We'll go through the various options we can set in this view, and this depends a bit on the measurement type, but this interface is pretty much standardized across different measurement types. On the left-hand side, we can set the start and stop frequencies. By default, it's set to 100 Hz to 40 MHz. We can, of course, go down and up. We'll just leave this as default. We can set this type of sweep if it's linear or logarithmic, how many points we want to do per sweep. More points, of course, increases the sweep time. We can change the source level, which is the power of the generator, up to 13 dBm. And we can reduce that depending on our requirements. Now, if we increase the source level, we might risk introducing AC bias effects onto our capacitors, or we might risk overloading channel 1 and channel 2, the inputs of the Bode 100. You have to select your source level carefully to not introduce any nonlinearities, to not overload the receivers, but we also want to keep the source level high enough as to increase the noise suppression. We do also have a receiver bandwidth, so the narrowness of the receiver filter, and that can increase our measurement resolution, which can be very helpful if you want to have finer measurement detail. For us, 300 Hz is fine for this case. We can see what that changes later on. We can also change the impedance reflection setup by going to the top spanner, and we can change various parameters here. We can see the output is running through this 50 ohm resistor. We're using the external references for channel 1 and channel 2 with the high impedance setting of 1 mega ohm, 1 mega ohm. There's not terribly much we can change here for this impedance adapter. We can also see that I can't start any measurements yet. I can't do any continuous or single sweeps, and this is because a calibration is required in every case for this measurement type. We can do a full range calibration for the entire frequency range of the instrument, or if we're only interested in a certain frequency band and want to keep our calibration and sweep time shorter, we can do user frequency range calibration. We'll just go with a full range calibration, so I'll click on that, and here we can see what we have to do. We need to do an open calibration, a short calibration, and a load calibration. If I expand the advanced settings, we can change two parameters. One is that of the load resistor. I'll be using a 100 ohm plus minus 1% tolerance resistor. It might be better to use a lower tolerance resistor if available. I'll just go with the 1% in this case, as well as we can change the short delay time. So if the short you attach to your measurement setup introduces a tiny bit of delay, a couple of picoseconds, you can input that here. In our case, we'll leave that at 0 and we'll leave the load resistance at 100 ohms. So now let's perform the calibration. The first one I'll go with is the open calibration. And for this, what I've set up, I've tightened this screw nut on the left-hand side of the B-SMC, which means these two contacts are not touching. This means we have an open calibration. There's no electrical connection between the left contact and the right contact. Going back to the Bode 100, Bode Analyzer Suite, I'll click on Open and start the calibration. The speed of the calibration depends on your frequency range and, of course, on your receiver bandwidth. Now let's do a short calibration. And for this, I've now released this spring that the left contact is directly touching the right contact and we have a short. Keep in mind, the amount of pressure you apply between the left and right terminal will change the contact resistance. So I'm just relying on the spring force itself to provide that contact force. Now, this isn't entirely ideal. If I use my hand to squeeze these two contacts together, I get a far lower contact resistance. But for the sake of this video, I'm just going to rely on the spring force so we get a repeatable measurement. With that in place, I'm going to click on short and we'll start the short calibration. Next, after that has been completed, we need to do a load calibration, and you can choose effectively any load resistor you want. What I'd suggest doing is choosing a load resistor that's similar to the package size you're going to be testing. So we'll be looking at roughly 0603-ish size capacitors. Of course, we'll go a bit larger with the electrolytics and tantalums. So I'm going to choose an 0603 load resistor with 100 ohms. And in my case, I happen to have some 1% lying around. And for this video, this will be good enough. But keep in mind, a good calibration will give more accurate measurement results. Finally then, we need to do the load calibration. As you can see here, I've now popped in a 100 ohm 0603 1% tolerance resistor, and I'm relying on the spring force to clamp the left terminal through the resistor to the right terminal, and this will be our 100 ohm load. Going back to the calibration, I'm going to click on Start on the load calibration. This will run through fairly quickly, again because of our fairly high receiver bandwidth, and I'll click Close. I still have the resistor in place, so if I start doing a continuous measurement on the top left-hand side, what we'll see, the red curve is the impedance magnitude and the blue curve is the impedance phase. I'll go to View and then Auto Axis Placement 1 axis per chart to make this a bit better. What we want to see, what we should see, are completely straight lines for this resistor, which means we've got at least by the looks of it, a fairly decent initial calibration. We are 100 ohms all the way through from 100 hertz all the way up to 40 megahertz for our frequency range, and our phase is at 0. I can, of course, right-click and then go Auto-Optimize, which will change the scaling of our curves. And we can see now the y-axis scaling has changed, and we can see we have up to 100.03 ohms at the top and down to 99.97 ohms at the bottom. So we have a pretty good tolerance on that 100 ohms across our frequency range, and we've performed our calibration. And this is something you should verify. Another thing to verify is what your receivers, your channel 1 and channel 2 receivers at your inputs are receiving, and we can see that on the bottom side of the screen. The green bars show the receiver indicated signal strength that is being received. So we've arbitrarily set a signal source level of 8.5 dBm, and we're getting a third or even less signal strength. So we could increase that, but keep in mind it's not just about the receiver signal level, it's also for overdriving, exciting any nonlinearities on our measured components. For now, we'll just leave this. I'd suggest anytime you change your source level, your receiver bandwidth, or any other parameter of your system you're measuring, you should recalibrate. So we'll leave this for now, and I'll just stop our measurements. So now that we've got our calibration set up, we can finally get to measuring some components. The first capacitor I'd like to test is a 1 microfarad, 20% tolerance, 16 volt rated X5R, so a class 2 multi-layer ceramic capacitor in an 0603 Imperial package, and you can see I've mounted that here in the B-SMC, and this is currently in there ready to test. If we go to the manufacturer parts page, this is the part number, and we can see some of the specs down below. Again, 1 microfarad, 20% tolerance, 16 volt rated, 0603 package size, and an X5R type dielectric. We'll compare this later on as well, but the manufacturer, of course, provides their own data and their own measurements for this specific capacitor, and of course for others as well. For instance, the impedance versus frequency curve, the equivalent series resistance versus frequency, DC bias effects, AC voltage effects, and so on, as you can see in video number 114 as well. But for now, let's do the measurement. So going back to our Bode analyzer suite, all we have to do now is click on continuous measurement. And we can see the impedance measurement has now run through, and I'll just click stop for now, and we can see the characteristic impedance curve of a capacitor. At low frequencies, we have this on a logarithmic scale straight line going down, which indicates a capacitive region. Then we hit this notch at the bottom where we have our self-resonance, where the ESL and the capacitance of the capacitor resonate each other out. They cancel out, and we're left with the ESR at that frequency of the capacitor, after which we have this upwards rising slope, which is the inductively dominant range of the capacitor, which is dominated by the ESL, the equivalent series inductance. This is looking at the impedance magnitude, but we can also look at the impedance phase below. As is typical for capacitors, we have a minus 90 degree impedance phase shift. Then we hit the self-resonant frequency, where we flip our phase through that transition. So we go through the 0 phase mark around the self-resonance point, and then we flip to the inductive region, which is close to positive 90 degrees of phase. So this is pretty cool to see. With a very simple calibration, we've now measured very simply our capacitor. We can change the source level. Let's decrease that to 0 dBm and see if this measurement changes. I'll click on single, and we can see the self-resonant changes a tiny bit, but we can also see there's not particularly much detail in this self-resonant area because our receiver bandwidth is very wide. So I'll change the receiver bandwidth to 30 Hz, which will make the sweep take longer, do a single measurement. We can see the sweep is slower, but we get more measurement resolution. Now, it's important to check your source level again to see if you are measuring correctly the parameters you want to measure. You're not exciting any non-idealities or overdriving anything. And we can see here we get a tiny bit more resolution. What we can do is I can take one of these cursors, I can drag it along, and I can place it either manually at the minimum, or I can just right click, select cursor 1, find minimum. And that'll then automatically make, in this case, the cursor jump to the impedance minimum. The impedance minimum happens to be at 4.5-ish megahertz with a minimum impedance of 10 milliohms. Remember, our impedance measurement technique, this one is only optimum around 20 milliohms, so there could be some error in this measurement, of course. There might be also contact resistance in this region, but for now we can estimate we have about 10 milliohms at self-resonance of ESR, and the self-resonance happens at about 4.5 megahertz. Going back to the manufacturer page, let's check out their frequency characteristic, impedance magnitude versus frequency, and if we look, their self-resonance is actually slightly higher at 7 megahertz, but the ESR at that point is also about 9 or 10 milliohms, so that's pretty good. The self-resonant frequency will be off a tiny bit because we do have possibly uncalibrated inductances, which will add to the overall ESL and therefore push the self-resonant frequency down. So we are actually measuring below that, it's about 4.5 megahertz, because we might have more inductance than they did in their measurement. But we're getting a rough idea that our resonant frequency is about 5 to 7 megahertz, and we're getting an ESR at that point of 10 milliohms, and that confirms somewhat with the manufacturer, so that's already pretty decent. The Bode 100 itself has some quite nifty other tools. If we go to measurement at the top left, click add measurement, we can choose different measurement types. On the right hand side, measurement impedance, we'll stick with that, but format we can change to RS, and this is the series resistance. If I right click auto optimize, this changes the impedance curve. I can use my cursors and we can scan along the ESR. And we can see that is actually also frequency dependent. The ESR does change quite a bit across frequency, and we can get that from the cursor values when we move the cursors around. Rather than looking at ESR, we can also look at the capacitance. If we select CS, right click, auto optimize, and then we can monitor the cursor and see that trace 3, which is currently set to capacitance, gives us about 920 nanofarads. This is a nominally 1 microfarad capacitor, therefore this is well within tolerance. This is without any DC bias applied, so it's well within the plus minus 20% along the frequency range, which is still capacitive. But you do see this capacitance value does change depending on frequency. Lastly, let's change the format to inductance, so LS, right click, auto optimize, and now we can check in the inductive range. So on the magnitude plot, that is this upward facing slope after the self-resonance, we can see we have an ESL of about 1.2 nanohenries with this measurement setup. Again, this does also change depending on frequency, but it's about 1.2 nanohenries, again, for this particular measurement setup. So we verified the ESR at about 10 milliohms, resonant frequency around 5 megahertz for this particular capacitor, capacitance of about 0.9 microfarads, and an ESL of 1.2 nanohenries. Let's go over to the next capacitor. Before we do that, I'll go to measurement at the top left and click on data memory and save our curves on our measurements to a new memory area so we compare that between different capacitors. So I'll click on new memory, and I'll give this somewhat reasonable name, and we can save that to memory and then compare that to other measurements. The next part I'd like to measure with you is a tantalum type capacitor. So a polarized type capacitor, oftentimes not viewed particularly favorably for various reasons. This one is also at 1 microfarad nominally, 20% tolerance. It's this time rated to 25 volts. Again, a tantalum capacitor, and the package size is a Tantalum A. Polarity, especially when you're DC biasing this, is important, and we have the positive, so the anode marked for this capacitor. Let's go over and measure this. Our measurement setup is exactly the same as before. I've changed the receiver bandwidth back to 300 Hz, and I'll click on single and we'll run a measurement. And the red trace in the impedance magnitude is our new tantalum capacitor, and the phase, the blue trace, is now the tantalum capacitor phase. Our previous measurements for the multilayer ceramic 0603, same nominal capacitance, are the green traces. So now let's see what differences we can see. Given that they're nominally the same capacitance, we can see the capacitive region up to about 40 kilohertz is roughly the same in terms of impedance magnitude. The phase is only similar up to about 1 or 2 kilohertz, but again, the impedance magnitude is very similar up to about 40k because they're both 1 microfarad nominally. However, after which, the series inductances and resistances start coming into play even more. Typically, tantalum capacitors will have a higher equivalent series resistance than multilayer ceramic capacitors, and that's what we're seeing here. We can see the red trace in the impedance magnitude is bottoming out. If we take our cursor, it's bottoming around about 2 ohms, this flat region from about 100 or 200 kilohertz. So a very, very flat ESR region, and far higher in magnitude than our 10 milliohm equivalent series resistance multilayer ceramic capacitor. So we're not getting very, very low impedance. We're limited up to a frequency range about 40-50 kilohertz if you want a low impedance with this tantalum capacitor. So if you're trying to filter a signal at 100 kilohertz, you know your impedance at 100 kilohertz or 500 kilohertz, you know your impedance of the tantalum capacitor will be higher than your multilayer ceramic capacitor in this particular case. Also, we're not really seeing an impedance dip or self-resonant frequency in this particular frequency range. We can see the ESR profile and the inductance profile is relatively flat from 200-ish kilohertz. If we extend the measurement range, let's say to 50 megahertz, and do another sweep to extend that a tiny bit, we can see we're maybe getting a tiny dip just above 50 megahertz. We're not terribly sure about that. The inductance will then start taking over after that. But the ESR dominates for a large part of this capacitor's frequency range, at least the one we can measure. Let's move this back to 40 megahertz so all our measurements stay the same. We can add various other traces, or for example, change the phase trace to be equivalent series resistance. And then again, we can measure our equivalent series resistance to be about 2 ohms and our capacitance to be about 1 microfarad, because this is a 1 microfarad nominal capacitor without any DC bias currently. So this already I find pretty interesting, and it's great to see actual measured real-world results for the tantalum and for the multilayer ceramic capacitor. So let's go to measurement, store that in a new memory. So given it a somewhat sensible name, just an addition looking again at the tantalum manufacturer's datasheet, and they happen to have these typical curves, not exactly for our part. So we're looking for a 1 microfarad 25 volt DC part. In an A case, they don't really happen to have that here, but just for the sake of interest, if we look at the impedance curve versus frequency, let's say for this 4.7 microfarad 10 volt DC rated tantalum capacitor, we can see this also has a rather flat ESR response in the range of about 1 to 2 ohms, all the way up to about 50 megahertz. Only then the ESL starts taking over with this ramp up after that frequency. So that's where the ESL takes over, otherwise a very flat ESR band, and before that, that rather narrow capacitive region. So that's nice that this measurement somewhat aligns with what the datasheet is showing, at least for a very similar part. And now let's move over to the aluminium electrolytic SMD capacitor. As a rather different example, now I've popped in an aluminium electrolytic capacitor, so a fairly bulky size, about 6.3 millimeters in diameter, so the leads are spaced further apart. We have a far higher capacitance at 220 microfarads nominal, 20% tolerance, and 16 volts rated. You'll typically use aluminium electrolytic capacitors as bulk capacitors. They don't have particularly favorable properties for high-frequency applications or high-frequency bypassing or decoupling. So we'll see what the impedance versus frequency looks like for something like this. Quite different, not only because of the much larger capacitance, but also generally the properties of a capacitor such as this. If you look at a typical manufacturer's datasheet for this particular capacitor, this is a Lelon VZL, we don't usually see impedance versus frequency curves for these types of capacitors. Rather, they'll tell you at a specific frequency, in this case 100 kilohertz test frequency, what impedance are they seeing. So we have a 16 volt capacitor, 6.3 diameter by 7.7 height. And we have a 220 microfarad capacitor, so we're looking in this row in this column. So we should be seeing about 0.32 ohms at 100 kilohertz. Going back to our measurement setup, measurement window, we'll go to home and start a new measurement with this capacitor now in place. Now the red curve is our latest measurement, yellow is the tantalum, green is the multilayer ceramic. And this is very much what we can expect. Our initial impedance profile is much lower, so the magnitude of the impedance in the low frequency range, because of the far larger capacitance compared to 220 microfarads to 1 microfarad, our impedance is going to be much lower for those low frequencies. Because this is an aluminium electrolytic, we also will have a very flat ESR profile before the ESL kicks in. So from about 10 or 20 kilohertz, we've already reached the lowest impedance we'll reach for this particular capacitor. So if I'll move my cursor over this, at 100 kilohertz, our impedance is about 170 milliohms, which is significantly lower still than the tantalum capacitor in this particular case. So it might, in certain cases, be more usable than the tantalum, although it is much larger, much bulkier, has far greater capacitance. So we have this very large band and broadband ESR range from about 10 kilohertz all the way to about 2 or 3 megahertz, and from which the curve now will slant upwards because the ESL, the equivalent series inductance of this aluminium electric capacitor, takes over. We can measure this by changing our trace to LS, series inductance, and we can see we're getting about 6.3 nanohenries of equivalent series inductance. Because this is a physically larger part in various dimensions, we can expect a much, much larger inductance than, for instance, for the smaller 0603 or for the tantalum capacitor. So I personally think this tool is super cool. We can actually do real-world measurements of capacitors, see what their frequency ranges are, what the ESR is, the ESL, compare different capacitors and see if they're suitable for our specific application. Just comparing these three different capacitor types very briefly, the multilayer ceramic, the tantalum, and the aluminium electrolytic, these have very, very different characteristics. This is due to their dielectric type, their package size itself, the lead spacing, physical size, and more. If we just look at the multilayer ceramic capacitor, we can see there's a pretty defined resonance and overall a lower impedance from a specific higher frequency. So above about 1 megahertz, this multilayer ceramic capacitor up to about 20 megahertz or even higher has a far lower impedance than the tantalum as well as the electrolytic. However, we do have this pretty defined sharp resonance, plus the multilayer ceramic capacitor is sensitive to DC and AC bias derating, can have microphonic effects and more. It might be suitable for digital decoupling of a certain frequency range, but it might not be suitable for audio due to piezoelectric and microphonic effects. Whereas the tantalum capacitor generally is fairly poor performing. It's got a very high ESR, but it doesn't have a very peaky response. So it doesn't have a pretty pronounced resonant frequency. It's far higher, but overall we bottom out at about 2 ohms of impedance. Whereas the electrolytic capacitor, okay, maybe a slightly unfair comparison because it has a 220 times larger capacitance than the other two capacitors, but it also has a fairly flat broadband ESR range and overall fairly respectable impedance given the package size. However, the package size and the composition itself is a limiting factor, so we only get down to about 150 milliohms of impedance. So again, quite different than our 10 milliohm or 50 milliohm multilayer ceramic capacitor. So this is just to hint at that we do need to choose the right type of capacitor for the right application. Even within the class of capacitor, there are many, many differences, and that's why we need to model them and measure them. What I'd like to do now is lastly extract the model parameters, so that's the capacitance, equivalent series resistance, and equivalent series inductance, import them into SPICE and see if our simulation aligns up with our measurement. We'll do this for the 1 microfarad 16 volt X5R 0603 multilayer ceramic capacitor and where we have the measurements for here. Now keep in mind, you should typically be doing this at a specific operating point. Let's say this capacitor hangs at the output of a switching regulator that runs at 1 megahertz, then you'd extract these values at 1 megahertz. As well as a certain DC bias, maybe 3.3 volts, maybe 10 volts, maybe a certain ambient temperature, that will all change these parameters that you're extracting. So we are creating a model now at a single operating point. And that is valid for that operating point only, but for many circuits it's a good overall approximation for a more broadband behavior. I'll show you how to do this very, very generally. So rather than picking a specific point, we'll follow the guidance given in the previous video, number 114, and the equations here. So the capacitance will look at the low frequency curve, which is this downward slope where the capacitance dominates. The ESR will simply look at the self-resonance point. So this is actually the lowest value of ESR. The value of ESR does depend on frequency, and the equivalent series inductance, the ESL, we can either calculate that at the self-resonance using one of these equations, or look at the upward slope after the self-resonance to get us the inductance. These are the ways I would do it if I didn't have the Bode analyzer suite and the Bode 100, but since I do happen to have the luxury of having this Bode 100, I'll just use the tools in there. For this, I'll change one of these traces to capacitance, and then I'll move somewhere in the capacitive region, and we can see the capacitance does change if you look at trace 2, the cursor here, but it's something around 950 nanofarads. So that'll be our capacitance. If I change to series resistance and I move it to my self-resonance point, approximately this will be something around 10 or 15 milliohms. Right now this measurement is showing 15 milliohms. And then my inductance, I'll change my trace to inductance and move to the inductive region. And we're seeing something like 1.2, 1.3 nanohenries. So 950 nanofarads of capacitance, 15 milliohms of equivalent series resistance, and 1.3 nanohenries of inductance. I happen to be using LT-Spice here, so all I've done, I've popped a capacitor, inductor and resistor in series. The order does not matter. I'll change the capacitance to 950 nanofarads, the inductance to 1.3 nanohenries, and the series resistance to 15 milliohms. To get the impedance, what I can do is I go to the Components tab at the top, select my current source, attach it one side to ground and the other side to my circuit, right-click on the current source, click Advanced, DC value is 0 and my AC amplitude is 1. V equals IZ, so if my AC amplitude is 1 of my current source, that means the voltage we measure here is equal to the impedance seen at this node, which is the impedance of the capacitor, is what we're measuring. So therefore I can run an AC simulation. I'll just click Run, which will make me edit the simulation command. Click on AC Analysis. I'm going to choose a fairly generic sweep. Start frequency 100 Hz, stop frequency 40 MHz, just like we had in our simulation, and click OK. Now if I probe this node, this will show me the impedance seen at that node. Looking into the capacitor, I'll change my axis to be logarithmic rather than the decibel scale. This is now what we see. I've pulled my measurement on the left-hand side to my simulation on the right-hand side. Again, this is at a single operating point with approximated values. I can get out my cursor and LT-Spice. If I move to 100 Hz, we can see I'm getting an impedance of about 1.6, 1.7 kiloohms, and my measurement I'm getting about 1.6 kiloohms. My resonant frequency in LT-Spice is somewhere around 4.5 megahertz. If I look at my measurement on the left-hand side, this is also around 4.5 megahertz. My impedance at about 40 megahertz is about 320 milliohms, and in my measurement at 40 megahertz, the impedance is also 320 milliohms. So just by looking at the self-resonance, the capacitive region and the inductive region, we've extracted the model parameters, and we can see both the magnitude and the phase seem to align quite well for this specific operating condition. So with this very, very simple model, not even including the leakage resistance, we get quite a good fit between measurement and simulation. Lastly, what we can also do in the new Bode Analyzer suite, as of the release of this video, we can go to Measurement and add Circuit Fit. The Bode Analyzer suite can actually do this for us. This can get very, very complex. We just need a simple fit. So I'll choose my data source is the impedance value in ohms. My model type, I can choose different types of models. What we've been doing is actually Model D, but we could also use Model G if we also want to model the leakage resistance. We'll just choose Model D for now, which is series resistance, series inductance, and capacitance. We can choose different fitting options, and then we can click on Start Fit. And this is what has been extracted using the circuit fit parameters of the Bode 100. We can see the relative measurement errors. Equivalent series resistance is about 80 milliohms, 1.4 nanohenries series inductance, and 930 nanofarads. So slightly different to what we extracted, just eyeballing it. But this is a very quick and pretty cool tool, I think, rather than having to do this manually. Let's just quickly try out Model G to see what the leakage resistance would be, and click on Start Fit again. And we get the same values for RS, L, and C, which is what we want and what it should be. And now we can find that we have a leakage resistance of about 41.5 kiloohms. So we could add that in to our model as well if we wanted to. Thank you very much for watching this video. I hope it was helpful, and I hope it showed you some insights into capacitor measurement and modeling, at least the very basics of it. Of course, that we can go far, far deeper. This hopefully serves as a good introduction. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest embedded systems, hardware design, PCB design, and test and measurement videos. Thanks again for watching, and I hope to see you in the next video. Bye-bye.